The fundamental theorem of algebra states that in a polynomial with degree n, the number of complex roots is equal to the sum, or is the degree n tells you the number of complex roots. So if it's degree 5, then you're going to have 5 complex roots. If it's degree 6, then you're going to have 6 complex roots. The number of complex roots is equal to the sum of the real and imaginary roots. So imaginary roots are where you can't see where it crosses the x-axis. Real roots are where it crosses the x-axis. So example 1, how many complex roots does it have? So complex roots by the fundamental theorem of algebra is just the number, the degree. So this polynomial has degree 2, so it's going to have 2 complex roots. This polynomial is degree 3, so it's going to have 3 complex roots. This polynomial, the last one, is harder to figure out because it's not written in standard form. However, if you FOILed these two, you'd get an x squared term. And then if you FOILed these two, you'd have x squared. So if you multiply x squared times x squared, it's going to be x to the 4. So this would be degree 4. Okay, also when we're going to talk about the fundamental theorem of algebra, it's important to know whether a function is even degree or odd degree. So instead of, this should actually be even degree functions, not just even functions, but even degree functions, odd degree functions. Because even and odd functions are something a little bit different, but even degree means that the exponent's even. So even functions have the same end behavior. Odd degree functions have different end behaviors. So on this polynomial, it is the minimum, it's starting at negative infinity from left to right, and it's ending at negative infinity. These are both going down. So this is the same end behavior. So this would be an even function, even degree function. The second one, if you're reading from left to right, this is coming from negative infinity, and it's going to positive infinity. So because it's going from negative to positive, they're different end behaviors. So this is an odd degree function. The third one, from the left, you're starting at positive infinity and you're ending at positive infinity. These are the same, so it's an even degree function. These two are both ending at, or it's starting at negative infinity and ending at, or starting at positive infinity and ending at positive infinity. So that's even. And this is starting at positive and ending at negative, so that's odd. And this one's starting at negative and ending at positive, so that's odd. Okay, next part. Sketch an even degree function that has no real roots. So it has to have the same end behavior and not cross the x-axis. So here is an even function and it doesn't cross the x-axis. That's my example. Then try to sketch an odd degree function that has no real roots. So if you're starting at infinity, positive infinity, how do you end at negative infinity without crossing the x-axis? So this is impossible. So what that's telling us is that if it's an odd degree function, it has to have at least one real root. So if I'm looking back at these examples up here, this odd has at least one real root. This odd has to have one real root. This odd has to cross the x-axis. All odd functions have to cross the x-axis. Every odd degree polynomial must have at least one real root. Even degree polynomials may not have any real roots. Some even degree functions have real roots, some do not. Imaginary roots and irrational roots must come in pairs. That's another. So if it's degree 1, the number of complex roots is 1 because it's degree 1. So the number, if it's an odd degree, it has to have one real root. And so if it has one real root, it must have 0 imaginary roots. Then we'll do degree 2. So degree 2 has 2 complex roots. So I'm just going to fill in this row right here, because remember the complex roots. The number of complex roots is equal to the degree of the polynomial. So when you're filling out this chart, when you're looking at each degree function, you have to recognize that imaginary roots come in pairs. You cannot just have one imaginary root. You either have to have 0 imaginary roots, 2 imaginary roots, 4 imaginary roots, and 6 imaginary roots, etc., because they come in groups of 2. So, and another thing you have to look at is the number of real roots plus the number of imaginary roots has to add up to the number of complex roots. So in our first row, 0 plus 1 adds up to 1. That works. So if I put, I could have 0 real roots and 2 imaginary. That's possible because remember, an even degree function might not have any real roots. And 0 plus 2 adds up to 2. And this works because you can have 2 imaginary ones because they come in groups of 2. So now I could put, could this be 2 and this be 0? Could you have 2 real roots and 0 imaginary? Yes, it works. But if I do 1 real and 1 imaginary, that does not work because you cannot have 1 imaginary root because they come in groups of 2. So that's not possible. So I'm going to erase that. So you could either have 0 real, 2 imaginary, or 2 real, 0 imaginary. Okay, if it's degree 3, remember this is odd, so it has to have at least 1 real root. So if it has 1 root, 1 plus 2 is 3. So, and that works because 2 can be, imaginary roots can have to come in groups of 2. So can you have 0 real roots and 3 imaginary? No, because you can't have an odd number of imaginary. Let's try another combination. Could you have 3 and 0? Yes, because 3 plus 0 adds up to 3, and number of imaginary roots is even. So the numbers in this column must always be even, if you're seeing that pattern. Okay, now let's try 4. So you can have, it's an even degree function, so even degree functions might have 0 real roots. That would make 4 imaginary. You could have, can you do 1 and 3? No, because this 3 can't be odd. So you could do 2 and 2. You could also do 4 and 0. 5 is an odd number. It must have 1 real root. So if I had 1 real, it'd have to have 4 imaginary. Now these numbers all need to be even over here. So it might be easier to fill in 4, 2, 0 and make this be 1, 3, 5. And 6, it'll be easier if I fill in 6, 4, 2, 0. So this would be 0, 2, 4, 6. So look at the pattern here. If it's an odd degree function, the number of possible real roots are odd numbers. And if it's an even degree function, the number of possible real roots are even numbers. And then no matter what, the imaginary ones are always even. Given the function, determine the number of complex roots. Then use your graphing calculator to determine the real roots. Then list the number of imaginary roots. So this one has 3 complex roots. So what I'm going to do, I'm going to determine the real roots on my graphing calculator. So I'm going to put this in my y1, 5x cubed plus 2, and find where it crosses the x-axis. So I think the easiest way to do this is I'm actually going to put 0 in for y2. So I'm going to put y2 as 0, and I'm going to see where those 2 crossed. So again, just from the previous lesson, you do second trace intersect, and you slide your cursor to where they intersect and press enter 3 times. So this real root is negative 0.73 or 0.74. And it crosses 1 time. So if that means that there's 1 real. So if there's 3 complex solutions, 1 is real, this means that 2 have to be imaginary. So I'm going to do the same thing for letter B. So the number of complex roots is degree 4. And now I'm going to plug in my calculator this into y1. So I'm going to plug in y1, negative 2x to the 4th. So you should be trying it on your calculator right now too. Minus x minus 6, and press pause if you need to slow down. And in y2, I'm going to put 0. So I'm going to put 0, and I'm going to see where they intersect. So second trace, intersect. And I'm going to press enter 3 times. So looking at my calculator, they don't intersect. So there's 0 real roots. So that would mean if there's 4 complex and 0 real, there has to be 4 imaginary, because the number of real plus the number of imaginary has to add up to the number of complex roots. Okay, I'm going to do this last one. It has to have 6 complex solutions. So I'm going to put, in my y1, I'm going to write the function. In my y2, I'm going to put 0 and see where they intersect. So 2x to the 6th plus 3x to the 4th minus 5x so these intersect twice. So the real roots are at 0 and 1. So there's actually 2 real roots. So that would make, if it's degree 6, if the number of complex solutions is 6, the real roots are 2. That means that there has to be 4 imaginary. Okay, in example 3, a polynomial with rational coefficients has roots at 2 plus root 3 and negative root 5. Give 2 additional roots. So imaginary and irrational roots come in groups of 2, and they come in conjugates. So the other root would have to be 2 minus root 3. And the conjugate of negative root 5 is positive root 5. Same thing with imaginary roots. They have to come in groups of 2, and they also are conjugates. So if positive root 3 is a root, then negative root 3, or negative 3i is a root. If negative 2i is a root, then positive 2i is a root.